Welcome to the final session for today. So we have Hao Wu from MIT talking about conformal restriction, the chordal case, and the radial case.
Okay, first of all, I want to thank the organizer for the invitation. It's my great honor to give a talk at this conference. My talk will have 4 parts. The first part, I will give an introduction on Brownian intersection exponent and the conformal restriction. The second and third parts are ideas of the proof of the main result, and in the fourth part, I will give some recent results about this story. So first, Brownian intersection exponent. Now let us consider two independent planar Brownian motions. Their starting point has distance 1. And we run both of the Brownian motion after time t. We want to calculate the probability that the two paths avoid each other. And we can guess that this probability will decay as a power law of t. And we define this power as C11, and we call it as the whole plane intersection intersection exponent for two independent Brownian motions. And next, we can generalize this exponent a little bit. Now we consider this is a simulation of two Brownian motions conditioned to avoid each other. And next, we can generalize this exponent a little bit. Now we consider we have 2 packets of Brownian motion. The first packet has n Brownian motion. The second packet has m Brownian motion, and all of them are independent. So now we run all the Brownian motion after time t, and we still want to calculate the probability that the first packet avoid the second packet. And again, this probability will also decay like a power law of t, and we define that exponent as Cnm, and this is what we call the whole plane intersection exponent between one packet of n Brownian motion and another packet of m Brownian motions. And next, there's a related notion called half-plane intersection exponents. So the story is very similar as above, and the only difference is, so now we have 2 packets of Brownian motion. Their starting distance is 1, and their distance from the real line is also 1. And we'll calculate the probability that the 2 packets avoid each other, and at the same time, we also require that all Brownian motions stay in the upper half plane. So of course, this probability will be much smaller than the above one, and this probability will also decay like a power law of t, and we define it as cos tilde 11 or cos tilde nm. And since the probability will be much smaller than the above one, so the exponent here will be much bigger than the above one. And this is what we call half-plane Brownian intersection exponents. So the question is, what are these 2 exponents? So here is explicit formula for these 2 exponents. So this formula is conjectured by Duplantier and Kwong in 1988, and they proved by Lawler, Schramm, and Werner in 2000. And today I won't talk about how to prove these formulas. I will talk about something very closely related to these 2 exponents, and it's called conformal restriction. So now I finish introduction about intersection exponent, and next I will introduce what is a conformal restriction. I prefer to start with an example. So now let us consider we have a Brownian excursion in the upper half plane. So roughly speaking, it is a Brownian motion, but going from 0 to infinity in the upper half plane, and it doesn't hit other boundary points. And for this Brownian excursion, it has 2 important properties. The first is called scaling invariance. So suppose this E is our Brownian excursion. For any positive constant lambda, we know that lambda E has the same law as the excursion itself. So Brownian excursion is scale invariant. The second property is called restriction property. So for this property, we mean that we consider this Brownian excursion in the upper half plane. We fix the deterministic set A here. And now we condition on this excursion to avoid A. Since this is a Brownian motion, we know that the conditional law for this excursion has the same law as excursion in the remaining region. So it's just a Brownian excursion in H minus A. Or we can put this property in another language. So now we define a conformal map phi A from H minus A onto the upper half plane. Fix our range at the infinity and has derivative 1 at the infinity. And then condition on this event, we know that the image of the excursion has the same law as itself. So this is the restriction property for Brownian excursion. And moreover, we also know that if K is a Brownian excursion, we know the probability for this excursion to weight set A is phi A prime 0. So this is something well known for the Brownian excursions. And our motivation to introduce chordal conformal restriction is parallel to the ideas here. So now we introduce what is our chordal conformal restriction sample. So it is a random set K satisfies a random set K satisfies chordal conformal restriction property if it has the following two properties. First, it is scale invariant. So for any positive lambda, lambda times K has the same law as K itself. Second, it has restriction property. So condition on K await set A, then phi AK has the same law as itself. And at least we know that the Brownian excursion satisfies these two properties. So there is some random set satisfy these two properties. And also we know that the union of n independent Brownian excursion also satisfies this property. And we can calculate the probability that if K is the union for n independent Brownian excursion, then the probability for this K await A is phi A prime 0 to the power n. So at least we know that we have many random sets have this property. At least they are indexed by this integer number n. So the next question is, what's the whole family that satisfies these two properties? And here is the answer. So this theorem has two parts. The first part is called characterization part. So a chordal conformal restriction measure is fully characterized by a positive real beta. And this beta related to the random set in this way, in this equation. The second part is called existence. So this random measure exists if and only if there is a lower bound for this beta. So as our previous example, if K is the union of n independent Brownian excursions, we know that it corresponds to this sample when beta equals n. So here we also have a motivation that for this random set, if we have a bigger beta, it corresponds to a random set will become fatter. Okay, so this is the story about chordal conformal restriction. So why I say it is chordal? Because in this story, we always consider a random set connecting one boundary point to another boundary point. And the next natural question is, what's the radial counterpart conclusion for the radial case? For radial case, we mean that now we need to consider a random set that connects one boundary point to an interior point. So here is the story for the radial case. So now we consider a random set K. It is in the unit disk connecting the boundary point 1 to the interior point origin. And we want to copy what's the story for the radial case. And now, first of all, we don't have scaling invariance in the radial case anymore, but we still have restriction property. So in the radial case now, the restriction property becomes this one. It's very similar to the chordal case. So for any fixed deterministic set A, condition on K await A, we define the conformal map phi A. So it is unit disk minus A onto the unit disk. And normal fix the origin and 1. Then this image of the random set under phi A should have the same law as itself. So this is the radial counterpart for the restriction property. And then our question is, so this gives us a definition for the radial conformal restriction property. So what's the question is there any random set satisfy this property, and what's the whole family that with this property? And here is the answer. So the answer also has two parts. The first part is the characterization part. So a radial conformal restriction measure is fully characterized by a pair of real numbers, alpha beta. And this alpha beta is related to this random set in this way. The second part is the existence. So the measure exists if and only if there's a lower bound for beta and upper bound for alpha. And here I want to explain a few more words about these two equations. So first, in the radial case, when we define this conformal map phi A, it is from unit disk minus A onto U, fixed origin, and at boundary point. And for this conformal map, we know that the derivative at the boundary point is always less than 1. And the derivative at the interior point is always greater than 1. And we go back to the relation here, we see that the left-hand side is a probability. The right-hand side is a product of two derivatives to some power. So first of all, the right-hand side should be less than 1. So of course, it can't be true for all possible alphas, because if alpha is very large, beta is not large enough, then the right-hand side will be greater than 1. So this gives us the idea that there must be an upper bound for alpha. So alpha can't be too large. Otherwise, the right-hand side will be greater than 1. And this is the second part. The second part shows that the exact lower bound for beta is the same as the chordal case, and the upper bound for this interior exponent alpha is given by this formula. Okay, so this is the story about the radial conformal restriction. Before I go to the idea of the proof, I will explain what's the difference between the chordal case and the radial case. So in the chordal case, when we define chordal conformal restriction, we have two requirements. The first is conformal invariance. Second is restriction property. And the answer is there is a the random set is characterized by one real positive beta. So there's 1 degree of freedom. And in the radial case, since we don't have requirement counterpart to the scaling invariance, so now in fact we have one less restriction. So this explains why we have one more degree in the answer. Okay, so this is the relation between the chordal case and the radial case. And next we can go to the idea of the proof. So first I will prove the characterization part. So the conclusion says a chordal conformal restriction measure is fully characterized by a positive real beta. And the random set and the beta are related through this relation. So the first observation is, if the random set satisfies this relation for any set A, then it is already satisfies chordal conformal restriction property. So what we only need to show is why there is only 1 degree of freedom. And the idea of the first step is we calculate what's the probability that this random set hit a small bore along the boundary. So of course, this probability would decay as epsilon goes to 0. And in fact, we can derive that from restriction property. This probability will decay like epsilon squared. And then we normalize this probability by epsilon squared and take the limit. Then this limit will convert to a limit. We call it as lambda x. And here we can say that this limit will depend on where is the center of this ball. And then this is the first step. And second step, we can use the scaling invariance to solve this limit function lambda. So because we know that the random set K is a scaling invariant, so for any fixed x and y, two positive real numbers, now let us calculate what's the probability that this K hits a small bore centered at x times y. By definition of this function lambda, we know that it will decay like lambda xy times epsilon squared. But on the other hand, we know that this random set is scale invariant. So this means this probability also equals the probability that if we normalize everything by x, by y, so from here to here is the scale invariance. And again, by the definition of this limit, we know that it will decay like lambda x times epsilon square over y square. So this gives us a relation between lambda xy and lambda x times over y square. So this tells us by scale invariance, we know that this lambda xy should equal to lambda x over y square. So this from the relation here, we already know there is only one solution for this lambda. So this lambda function should have the form in this way. And there's only 1 degree of freedom. So this is, sorry, maybe this is not how they prove this theorem in the paper, but this is the idea that we can apply it parallel to the radial case. Okay, so now this story, so the scaling invariance explains that there is at most 1 degree of freedom. So this is the proof for the characterization part for the quarter case. And next, we can use the parallel idea to prove the characterization part for the radial case. So for the radial case, the conclusion is a radial conformal restriction is fully characterized by a pair of real numbers, alpha and beta, in this way. So the same observation as before. If the random set already satisfies this relation here, then it satisfies the radial restriction measure. It satisfies the radial restriction property. And the only thing we need to prove is why there are 2 degrees of freedom. The first step is the same as before. We calculate the probability that this random set hits a small ball on the boundary. This probability will decay like epsilon squared. We normalize this probability, take the limit, define a function lambda x. So the first step is the same as before. But now, in the previous case, in the second step, we use scaling invariance to solve this lambda x. But in the radial case, since we don't have scaling invariance, we have to find some other ways to solve this function lambda x. And the idea here we use is called commutation relation. So what we do is now we calculate the probability that this random set hit 2 small balls. We can see that this probability will decay like epsilon squared times delta squared. And we normalize this probability by epsilon squared, delta squared. And now we want to take the limit. So we want to let epsilon and delta goes to 0. But since now we have 2 small quantities, one is epsilon, one is delta, so we can choose to first take which to 0. So the commutation relation here is we can first let epsilon goes to 0, and then let delta goes to 0. And the limit would be the left-hand side in this relation. And then we can change the order. We first let delta goes to 0, and then let epsilon goes to 0. The limit is the right-hand side here. And next, we need to verify that we are allowed to change the order of the limits. So in other words, the limits taken both ways should be the same. And then we know that the left-hand side equals the right-hand side. And here in this relation, this big F and the big G are just the explicit function in x, y, so you don't need to worry about it. They are just explicit. And then from this commutation relation, we can solve the function lambda. Here is the solution of this function. And from the solution here, we see that we only have 2 constants, C0 and C2 there. So this tells us for the radial case, we have at most 2 degrees of freedom. And one thing I want to mention here is, in fact, we can also apply the same method for the chordal case. So we can also calculate this commutation relation for the chordal case. And we will also solve a 2 degree freedom thing. And it is the scaling invariance that exclude 1 degree of freedom in that case.
What are the F and G?
They are just the explicit function in x and y, and I can't remember. Okay, so this is the proof of characterization for the radial case. Okay, and next I will talk about how to construct all possible alpha and beta for this random set. And to this, inevitably I have to introduce what is an SLE curve. So before this, we have nothing to do with SLE curve. And now I have for the proof of the existence part, we will involve some calculation for the SLE curve. So we have already seen it several times from the previous talks. So a chordal SLE curve is just a random fractal curve in simply connected domain from one boundary point to another boundary point. It is introduced by Odette Schramm as the candidates for the scaling limit of discrete models. So we can define it as the random curve that with the following two properties. First is it satisfies conformal invariance. So suppose this curve is in simply connected domain D from A to B. Phi is a conformal map. Then the image of this curve under phi should have the same law as itself. Second, this curve satisfies domain marker property. So suppose we have a curve in D from A to B. Given the first part of the curve, the future part of the curve has the same law as a SLE curve in the remaining region from the tip to the endpoint. This is called domain marker property. So here we can see that these two properties are very closely related to the scaling invariance and the restriction property for what we discussed before. So as I said before, this random curve. So another remark is these two properties are natural properties from discrete models. So because we want to study the scaling limit of the discrete model, so that's why we introduce this random curve studies with these two properties. Okay, so this is SLE curve, and we know that with these two properties, there exists only a one parameter of growing process. It's called SLE kappa with these two properties. And when kappa is less than 4, that corresponds to simple curves. And since in my talk I only care about SLE asserts, so I will focus on simple case. As I said before, SLE curves are introduced as the candidates for the scaling limits of the discrete models. Since their introduction, they have been already proved to be the scaling limits in several cases. So SLE2 is the scaling limit of the loop erased random walk. SLE3 is the scaling limit of the interfacing critical Ising model. SLE4 is the scaling limit of the level line of discrete Gaussian free field. And one more thing I'm interested in the talk is SLE asserts is a conjecture to be the scaling limit of self-avoiding random walk. So it is still open, but we know something that is related to SLE asserts is the frontier of a frontal excursion is locally like SLE asserts. Okay, so now we have introduced SLE kappa. From the introduction, we can see that this standard chordal SLE kappa is always symmetric with respect to the axis. And next, I want to introduce what is SLE kappa rho. I don't want to introduce it as the solution as a linear equation, because I think if you know it, you know it. If you don't know it, you can't get anything from that equation. So I want to change another way to introduce SLE kappa rho. So for a standard SLE kappa, it is symmetric with respect to the axis. And for SLE kappa rho, in fact, it's not far from the standard SLE kappa. It just corresponds to, if rho is negative, means we have a attraction from the left-hand side, so the curve will be pushed a little to the left. And if rho is positive, it means we have a repulsion from the left part of the boundary, and the curve will be a little to the right. So SLE kappa rho is not difficult. So this is the standard SLE kappa, but a little to the left or a little to the right. And I will explain more about this rho in the last page of my talk. Okay, so now we can prove the existence part. So first is the chordal case. The existence part says the chordal conformal restriction measure exists if and only if beta is greater than 5/8. So first of all, from the calculation of chordal SLE asserts, we know that chordal SLE asserts satisfies exactly the restriction property with exponent beta equals 5/8. Next, for beta strictly greater than 5/8, we can construct the random set in the following way. As I said, when beta gets bigger, the random set will become fatter. So for a bigger beta, we can construct this random set in this way. We first sample its right boundary. And the law of its right boundary is SLE asserts rho process for some positive rho. So here we can say that the right boundary will be a little to the right. And then what sample is a condition on the right boundary, what sample is the left boundary. The left boundary is an SLA search. Rho minus 2 process. And then we fill everything between these two. And this gives a random set K. And by direct calculation from this construction, we can calculate that this random set satisfies exactly the chordal conformal restriction property with the given exponent, beta. And the beta and rho is related through this way. Okay, so the last part is why it doesn't exist for beta less than 5/8. So the reason, in fact, the idea of the reason here is clear because, as I said, as beta gets bigger and bigger, the random set will become fatter and fatter. So as beta gets smaller and smaller, the set will become thinner and thinner. And from the first step, we see that when beta equals 5/8, it corresponds to chordal SLA search. It is a simple curve, and we can't be thinner anymore. So this tells us 5/8 should be a lower bound. Okay, so this is the existent part for the chordal case. And next, we can talk about the existent part for the radial case. And you can see that the construction of the radial case is pretty parallel to the chordal case. So the conclusion here is the radial conformal restriction measure exists only if and only if the lower bound is the same. The lower bound for beta is the same as the chordal case, and this is the upper bound for the exponent alpha. So first of all, by the calculation for the radial SLA search, radial SLA search corresponds to exactly the radial conformal restriction set when beta equals 5/8 and alpha attains its max. And next, we construct beta strictly greater than 5/8 and alpha equals the maximum possible of this value. So the construction is very similar to the chordal case. We first sample the right boundary of this radial sample, and it is a radial SLA search row process. Given its right boundary, we sample the left boundary is a conditionally. The conditional law is a chordal SLA search, rho minus 2 process, and then we fill everything inside. And by direct calculation, we can show that this random set satisfies exactly the radial restriction measure with exponent beta, and the interior exponent equals C beta. And next, an important observation is once we have a random set with radial restriction property, and the two exponents alpha and beta, by adding a Brownian loop soup around our origin. So adding a Brownian loop soup with intensity C around the origin, and then we take the union of the two. We know that the union of the two also satisfies radial restriction measure. And now the new exponent is alpha minus C and beta. So here we can see that as long if we get to one possible alpha, we can construct all smaller alphas. And from the observation here, we can also see that if we can construct some random set such that this origin is on the boundary, it must be the largest possible alpha. Because once we get at one possible alpha, we put some Brownian loop soup. Then we can have a smaller alpha. So if this alpha is not the largest possible one, it is impossible that the origin is on the boundary. So this gives us the idea that once we prove the largest possible alpha, we can construct all smaller alphas. And the last part is the measure doesn't exist when beta is less than 5/8, and the reason is the same as the chordal case. Okay, so this is all the story about the radial conformal restriction property. And just one more thing I want to say is So for the radial restriction measure, in fact, this random set has two parts. One part is I called the head, and another part is I call this a tail. For this random set, if beta gets bigger, then it means that the tail gets fatter. And if alpha gets smaller, it means that the head will be bigger. So just some direct observation from of the shape of the random set and the two exponents. So this is all about the story for the conformal restriction property for the chordal case and the radial case. And next, I want to talk about some related questions, related properties. So,
Is it clear that it does not exist with alpha exceed this C beta value?
yeah, so the observation here is, since as long as, if we have a random set alpha beta, we put some Brownian loop soup, we will get a smaller alpha. So this tells us if this alpha is not the largest possible one, then the origin can't be on the boundary. And from the construction of C beta case, we show that the origin, from the construction, it's clear that the origin is on the boundary. So it should be the largest possible one. Okay, so this is the story about the radial case. Is there any question? Okay, next I will talk about some related properties. So first, consider we have two chordal conformal restriction sample K1 and K2. So the first one with exponent beta 1, second one with exponent beta 2. And if we just put them together, to put two independent samples together, the union of the two, of course, it is also a chordal conformal restriction measure. And the exponent would be beta 1 plus beta 2. But now we want to do something weird. So now we have two random sets. We condition on the event that these two sets avoid each other. And then we take the union of the two. The union of the two is still a chordal conformal restriction sample. And now the exponent becomes the half-plane intersection exponent. And we have a similar story for the radial case. So suppose we have two radial samples, and these two radial samples with the interior exponents as the largest possible one. So we condition on these two samples avoid each other, take the union of the two, and then the union still satisfies radial conformal restrictions property. And now the boundary exponent becomes the half-plane intersection exponent, and the interior exponent becomes the whole plane intersection exponent.
So you're taking a limit as those points go together.
Yeah. Yeah, because we have to start with a little difference between the 2 points. That otherwise the probability for them to avoid each other would be 0. Yeah. Okay. And next, I want to talk about some recent other works about the Hausdorff dimension of the cap point of restriction samples. So now consider K is a chordal conformal restriction sample with exponent beta. Ck is the cap point of this random set. So by cap point, I mean that suppose K is connected. The cut point of K is the collection of the point that if I remove this point, then it becomes disconnect. So this is the definition for the cut point of this set. And here just a few, some simple example. So suppose we have a simple curve. Then of course, every point here will be a cut point. And if we have a figure 8, then the point here will be a cut point. And in our case, we have a random site like this. And in this case, we can see that if we take the right boundary, the left boundary, the intersection of these two boundaries corresponds to the cut point of the random set. Okay, so this is the cut point of this random set K. And now we can prove that the Hausdorff dimension of the cut point is given by this formula. it is consistent with the previous result about the cap-point dimension of Brownian excursion. So the Brownian excursion corresponds to beta equals 1 case. And now we can prove all the custom dimension of the cap-point for this chordal conformal restriction samples. And this result is precisely derived from a joint work with Jason. And on this page, I'm going to talk about something that I do not understand. Even though I don't understand, I still want to talk about it. The first reason is I like this picture. The second reason is even though I don't understand, but Bertrand, Scott, and Jason are in the audience, and they understand what I'm going to say. So a third reason is now I will explain what is the role of this rho during the construction. So during the construction, we introduce the quantity rho. So we say associated to each exponent beta, we define a rho. During the construction, it's placed a rho when we construct the random set. But what is placed? Why this is the rho? So in fact, it corresponds to a quantum wedge weight. So it means, in fact, we can will a chordal conformal restriction sample as a quantum wedge with weight rho. It's actually the same rho as we introduced the construction of the random set. And if you agree on this, then let us check again what's the cut point dimension of this random set. So suppose this is a cut point. We zoom in around this point. Then in this neighborhood, we can see that in fact it corresponds to a welding of 4 quantum wedge. This one has the weight rho, this one has the weight 2, this one has the weight rho, and this one has the weight 2. So as the picture I draw there. And this tells us some relation between this quantum wedge weight and the quantum exponent delta. And from the KPZ equation, it will give us the Euclidean exponent x. And now we can say that 2 minus 2x should be the Hausdorff dimension of the cap points. And in fact, it is exactly the same as our precise proof in the previous page. And this is from the work by Duplantier, Miller, and Sheffield. Okay, so I don't understand what I just talked on this page. And if you have any question on this page, you can ask these 3. Okay, thank you very much.
Okay, so before we leave, I think Mike wanted to just say a few things.
I just wanted to let everybody know there are 2 changes to the schedule that we've had to make. So the first change is tomorrow afternoon, the order of the speakers has been switched. So instead of Christian Benish speaking before Vlad Ilimic, it's going to be reversed, and Vlad Ilimic is going to be speaking before Christian. The times of the talks, however, are unchanged. And then the final change is that on Friday, the conference will end at 3 o'clock after Vincent Bapar's talk. So there will be no afternoon tea on Friday. There will be no afternoon tea on Friday, and the TBA will not. There will be no lecture at that time. So the conference ends at 3 o'clock on Friday.
Okay, so can we just end by thanking all of the speakers from today?